In this video, we're going to look at reactive intermediates, and specifically we're going to look at carbocations. So we'll start with a carbocation. A carbocation is a carbon that has a positive charge. And I'm going to say a carbon with 3 groups and a positive charge. So carbon has a valence of 4. If it's deficient one of those groups, it'll have a positive charge, and that is a carbocation. Sort of the simplest carbocation would be the methyl carbocation. So it has 3 H's and is deficient that one group, and so it's got a positive charge. So the carbocation is a common intermediate in chemical syntheses, and so it'll be sort of between the reactants and the products. Sometimes we can isolate them, sometimes we can't. The carbocation is sp2 hybridized and is planar. So it's got a positive charge. I drew the 3 groups in plane, and this is an empty p orbital. So this is planar, and it is sp2 hybridized because it has those 3 groups around it. Since it has that empty p orbital and it has a positive charge, it's a great acceptor of electrons. So carbocations are electrophiles, which just means that it likes electrons. So they're very willing to accept electrons as an intermediate, and often will accept the electrons from another species to make a new bond. In terms of stability, there are a couple factors that influence. One is substitution. So that's how many neighboring carbon groups a carbocation has. So the most substituted would be with 3 carbon groups, right? To have a carbocation, I have to be deficient 1 group. So this is a tertiary carbocation, and that is more stable than a secondary carbocation. So a secondary carbocation would have 2 carbon groups, or 2 R groups, and 1 H, and that's more stable than a primary carbocation. Which would have only 1 R group. So this guy in the middle is secondary, and that guy on the end is primary. So as an intermediate, a tertiary carbocation is more stable than a primary carbocation. So with respect to substitution, what's happening there, and we'll look at an example of a tertiary carbocation. So the carbon in the middle is electron deficient, and these carbons on the outside can push electron density towards that deficient carbon through the sigma framework, and that's called the inductive effect. So a donation of electron density through the sigma framework of the molecule. So the more neighboring carbon atoms there are, the more electron density can be pushed towards the electron deficient carbon in the middle there, that carbocation, and so the more stable it's going to be. And that's why a tertiary is more stable than a secondary, than a primary, and then lastly than a methyl carbocation. The more carbon atoms there are, the more electron density is pushed through the sigma framework to stabilize that positive carbocation carbon in the middle. Another aspect of stabilization is something called hyperconjugation. This is a little bit involved, so I'm going to draw a picture here for us. So here's my carbocation carbon, and I'm going to draw the empty p orbital on it, and then its neighbor, and I'm going to draw 1 carbon here, and I'm going to draw what the actual orbitals that are part of those bonds look like. So if this is an H out here in a 1s orbital, this would be an sp3 orbital, and there's 2 electrons in it, and they're being shared between the carbon and the H. And then I'd have kind of the same thing down here and over here. So each one of those bonds are just sort of showing the sp3 type orbital, the hybrid that is overlapping with H to make those bonds. What happens in hyperconjugation is this bond between the carbon and the H lines up so that it is in plane with the empty p orbital on the carbocation, and electron density is sort of pushed over into that empty p orbital, a little bit like what a pi bond is. And it's a different way to push electron density into that vacant carbocation, forget I put a positive charge here, orbital, and so it's contributing electron density from this overlap of the sigma bond of the neighbor and the empty p orbital next door. So we have overlap of electrons in the sigma bond next door with, that's my with sign, the empty p orbital A of the carbocation. So this interaction, overlap of electrons in an adjacent bond with an empty p orbital, is called hyperconjugation, and it's another thing that can stabilize the carbocation. So the more carbon groups there are around it, the more possibilities for hyperconjugation there are. Lastly, resonance can help stabilize carbocation intermediates. So if we look at kind of a simple example, I'm just going to draw a line angle formula here. So I have a positive carbocation on the left-hand side there, and then I have a double bond next door. So because it's next door, I can get resonance stabilization. So the pi bond can move next door, and that shifts the carbocation to the right-hand side of the molecule. Now with Lewis structures we can show all of the different resonance structures, but what the molecule really looks like is sort of, I'm going to do it like a dashed line here, is that it has a partial positive charge on the left-hand carbon and a partial positive charge on the right-hand carbon. But the positive charge is not centered on only one atom, and so the charge is shared via resonance, which stabilizes the charge as opposed to it being isolated on one atom. So I'm going to say charge is shared over one or more atoms. So we've talked about resonance quite a bit now, but only pi bonds or lone pairs of electrons that are adjacent to the carbocation will be able to participate in resonance. So in summary, we looked at three factors: the substitution of the carbocation, we looked at hyperconjugation, and we looked at resonance. Those are the three factors that influence the stability of carbocation intermediates. You should watch this video again if you need to, read the section in your book, and then take the reading quiz.